In example 3, we're given a polynomial, and we are to determine the following. And we're going to just go through everything that we learned in section 2.2 and 2.3 to get all of these pieces in to analyze this function. So for example 3, once again, we have f of x equals 1/2 x to the 4th minus x to the 3rd minus 11/2 x to the 2nd plus 6x plus 6. It's in descending order, so the degree is 4. That's its highest power. The leading term is everything together of the highest power, so 1/2 x to the 4th. And the leading coefficient is 1/2, because that's the number in front of x to the 4th. The possible number of real zeros we could have will be 4. The possible number of turning points will be 3. So, because there's n minus 1 turning points. So we could have a maximum of 3 maxes and mins on our graph. We can sketch the graph on our calculator and use it to answer the rest. So on my calculator, let me get it entered. So my function is entered in. I'm going to hit graph. And it makes a nice W-shaped function, as we would expect for such a nice polynomial. Now notice we have 1, 2, 3 turning points. Our end behavior is increasing without bound to the left and to the right. And that we would expect that because we had a positive leading coefficient and an even degree. Now part F says the exact number of real zeros, or x-intercepts, is 1, 2, 3, 4. Which means that the exact number of complex zeros is 0. You can have at most 4 zeros, and these all happen to be real. To estimate the real zeros, you're going to second trace, number 2, and all of these zeros cross the x-axis, which means that all of them have a multiplicity of 1, because they're odd. And we're just going to have to put our spider as we come in from the left on each of these zeros, where the function changes from positive to negative, or negative to positive. So I'm going to drop my first anchor, then my second anchor. My first zero estimation is negative 2.84. Let's go get the next one. The next one is negative 0.66. And then the next one is 1.66, and the last one which is 3.84. We're to estimate the coordinates of all the turning points and classify them as local mins or maxes. So I'm going to hit second quit, pull my graph back up, and then I need to expand my screen just a little bit so I can get those minimums in there. So I'm going to go into Window, and I'm going to drop my Y minimum to negative 15. And I can see those minimums very nicely. So I'm going to get this minimum first. So second trace, number 3. And once again, coming in from the left, left bound, right bound, where I think it's turning at. So a negative 2. And that's a minimum. My next one will be this maximum. So second trace, number 3. Oh, sorry, second quit. Put my graph back up. Second trace, maximum's number 4. left bound, right bound, left bound, or guess, excuse me, it's going to be 0.5, and that's a maximum. And then my last one will be this minimum down there. So second trace number 3. Left bound, right bound, guess. So this turning point is at 3, and it is a minimum. Now we are to use this information to sketch our graph. So to start off with, once again, we know it's an even function where the leading coefficient a sub n is greater than 0. So I expect my graph to look like this on the endpoints. I'm going to go get my minimums and my maximums in. My minimums happened at -2, 12, and -12, excuse me, and at 3, -12. And I just looked over here and I saw that this minimum was at -12 on the y, so I could get those in there very nicely. So -2, -12, let's check the scale. It's a scale of 1. So -12, -10 is right there. -12 would be here. And then +3 across the x-axis is not a scale of 1. It's 1, 2, 3, 4. So it looks like there's 1, 2, 3, 4. So it looks like 1 would be located here. There's 2. So 3 would be located here. So 3, -12 is right here. And then the maximum, I failed to grab the y maximum, so let me go get that. So once again, second trace max number 4, coming in from left to right, left bound, right bound, enter. So my maximum is at 0.5 and roughly 7.53. So 0.5, that's 1/2, is right here. And 7.53 is roughly 7.5. It's 5, 6, 7, about right here. So there's my max. My intercepts, let me change my ink color to red. My x-intercepts are at -2.84, so this is -3 right there. So -2.84 would be right about there. Next x-intercept is -0.066. So here's -1. There's -1/2, so it's roughly right here. Then 1.66. So that's 1.5 at this place, so 1.66 is roughly there. And 3.84. So this is 3, this is 3.5, so 3.84 would be roughly here. So we have enough now to sketch this graph. It's going to come in from positive infinity on the y. It's going to drop down to this y-intercept. Whoa. Let me see if I can do a better job of that. There we are. And then when it gets to this minimum, it's going to turn and cross the x-axis, go to its maximum, drop, and hit the x-axis again, hit a minimum and turn. Back up. There we go. A rough-shaped graph, but we have it on our paper. And then we need to determine where it's increasing and decreasing. And remember, it changes from increasing to decreasing or vice versa at our turning points. So decreasing, coming from the left, is the function is dropping in value until it gets to this minimum. Then from this minimum to this maximum, it's increasing. And from this maximum to this minimum, it's decreasing. Then once again, from the minimum to the end behavior, it's increasing. So it's increasing from this minimum, x value, which is -2, until the maximum value of 0.5. And once again, this is increasing and decreasing. We give the x values in our intervals. And then it's increasing from this minimum's value, which is 3, to infinity, because it just keeps increasing. It's decreasing from -infinity to -2, to there. And it's decreasing from this maximum, 0.5, to this minimum, which is 3. Once again, decreasing uses x values on its intervals. And the end behavior, it rises to the left, or we would say it increases without bound on the left, and it increases without bound on the right. Another way we could say this is as x goes to -infinity. See, as x goes this way, y goes to +infinity, because y is increasing. Now, on the right-hand side, it also rises to the right. So we would say it increases without bound on the right. See here, I misspoke. This should be left. Up here, it increases without bound on the left. It also increases without bound on the right. And if we wanted to write it with these arrows, we would say as x goes to +infinity, so x is going this way to +infinity. As x goes to +infinity, our function goes to +infinity. So as x goes to infinity, y goes to infinity. Different ways we can express the same idea here.